Hello, and welcome to the SoilWatch solution demo video. This video is significantly longer than a company video and goes into a much greater level of detail. My colleague, William Ouellette, will take you through 4 aspects of our tech solution that we think you will be interested in. At some point in the future, we also hope to talk to you about why we refer to it as value-added carbon credits, and go into detail about the benefits to society, to food security, and to biodiversity that these projects have on the ground as well. But for now, over to William.
Hi everyone, my name is William. I'm the CTO of SoilWatch, and I'll be presenting to you today the set of MRV tools that we've come to develop with my colleagues. Most of those tools are at the prototype stage, but I think they show the promising work that we've been doing in terms of remote soil monitoring for the voluntary carbon market, as well as the potential to both empower land users financially and socially, as well as provide us a climate change mitigation solution through soil regeneration. The tools can be broken down into four categories, or at least into four big components. The first one being the scoping of areas of highest sequestration potential. Indeed, there is a lot of, let's say, excitement for the investment in soil carbon sequestration, and there's a lot of carbon credits being sold out there, but there isn't actually any tool offering for scoping areas or doing prior study as to where the projects should be deployed and developed in order to sequestrate that carbon in the soil. So, using environmental data sets, spatially explicit covariates, we hope to provide this scoping and this information to any project developers that would like to get started at sequestrating soil carbon and generating carbon credits, but does not know where to start. The second tool is an optimizer for soil field sampling locations. Indeed, if you go through scientific literature in this domain, you will find out that field sampling is an extremely costly and time-consuming endeavor, and we provide, so with the support of satellite imagery, we provide a way of finding out locations of optimal soil field sampling, not only to, well, first of all, to plan the logistics of the service, so where to sample at which locations and how to get there, but also sampling at locations which maximize the variability of your soil organic carbon. So even though at that stage we don't know yet how much carbon is in the soil, we can, based on texture of bare soil pixels in the image, we can find out the ideal spread of those samples. Then the third service would be the estimation of the soil organic carbon stocks themselves, or concentrations. This is the holy grail of the services, and it has a very high data quality requirements. So we need very good, timely, representative field samples to carry out such an analysis. But I will give you an illustration today that it's actually possible to do so with the support of remote sensing. And that, in fact, high-resolution satellite imagery, especially that of Sentinel-2 and its spectral bands, is an essential spatial covariate for prediction of soil organic carbon, and it's much more powerful than one would think. Finally, continuous monitoring of land management practices is the last sort of pillar that we offer. The reason for this is that we've identified the fact that monitoring soil organic carbon as a metric is quite difficult to do, and it requires really that the stars must align. So everything must be coordinated perfectly. You need to have the right data on the ground to provide a reliable estimations of soil organic carbon. But there's also a set of practices that is done on the land which also requires monitoring, because through proxy you can find out that, for example, if a reduced tillage or no tillage practice has been implemented, you are able to reliably say, depending on the region and the soil type, that this land management practice is actually going in the direction of building up carbon in the soil, even though you're not measuring the absolute amount of carbon that's being sequestrated, you know that by implementing this practice and by verifying that this practice is happening on the ground, you can effectively know that carbon is being sequestered and that the project is successful, or at least is on its way to generating carbon credits. So these are the four essential tools and prototypes that I'm going to be presenting today. So stay tuned for the following segment. Hi again. So we have actually compiled most of our outputs and the data from our prototypes into a Google Earth Engine app, as it's a very convenient tool to convey spatial information and analysis output. So as you probably guessed by now, and I've already mentioned it, Sentinel-2 is the sort of foundation, is the keystone to our services, in the sense that it provides, it's an open source satellite mission which provides data with very high revisit frequency, meaning that we can constantly monitor any location on Earth at the resolution of 10 meters, which is tremendous for the kind of work we are trying to do. So what we start by doing typically is already select our area of interest, which for this example will be Kenya, and we can start compositing or temporarily aggregating the data to create these single cloudless layers. So of course, this is not the imagery of any given day in Kenya, but it's a take. So it's basically one synthetic layer of valid cloud-free observations corresponding to the year 2020. So this is, if you zoom into any location in data, you will find out that the data is valid for the year 2020, but might not come from the same day. So this is just a median composite, meaning that we pick the median values of the temporal stack and we plot it at each location. So you see that you have a tendency for the areas around Lake Victoria to be green, which is more representative of the yearly landscape or the average of the landscape over the span of the year. Whereas if you go in the northeast or north parts, of course, you have very, very barren surfaces. So, of course, this is just a median value for the year, but we're in fact much more interested in exploring the bare pixels over the span of the year. So here, compared to the previous composites, you see there's a lot of data gaps. And those data gaps mean that those areas are covered by vegetation throughout the entire year. So we actually don't have any bare soil observations of those locations, which is fine. But it's already a nice way of decompositing the landscape and knowing which areas are exposed, or which soils, where our soil is exposed, to also know what are the likelihoods and the danger of soil erosion and land degradation. So this is sort of the starting point to our analysis, creating these synthetic soil composites. And what we end up doing is use this bare soil composites, use an additional layer on top, which is the bare pixel frequency. So how many times in the year has the pixel at a given location been observed to be bare? In this case, we see that there are quite some areas in the north that have a very, very bright value, which means that they're close to 100% of the time bare, whereas the areas that have no data are the ones that are never bare, and the areas with the low purple tones would typically be areas that have that are bare a couple of times a year, maybe even once a year. So this is typically agricultural zones where you have tillage that occurs or some kind of land preparation typically in the dry season. So so using these covariates as input and as well as temperature and rainfall information, which is also available through the Google Earth Engine, we're actually able to generate this kind of information, which is what we call a soil organic carbon sequestration potential zonation. These zones are they're basically the result of an unsupervised classification using meaningful environmental covariates. And we end up finding out that the country is essentially divided into three big zones from a soil organic carbon sequestration point of view. So the blue zones are the areas of high rainfall, typically more mountainous, very green and lush, but very, very, very low bare soil exposure. So that doesn't mean you cannot sequester carbon. Actually, quite the contrary. In fact, it's an area of high carbon sequestration potential. The only problem is that the leverage of remote sensing in those areas is quite limited, because typically you will be under canopies most of the time, so you don't have a direct observation to the bare areas. The red area, in this case, is an area of sequestration potential to a lesser extent, in the sense that they're basically the very low rainfall, high temperature areas of the country, meaning that in these areas you might have pastoralist activities and a lot of grasslands, but the sequestration rate in those areas would be extremely low. So what you could do, though, in the red areas is consider projects of carbon offsetting rather than carbon removal, where you actually try and preserve the remaining grasslands through sustainable grazing practices and pastoralist activities, which would also be able to generate credits. So yeah, this is more in a sort of conservation mitigation effort than an actual carbon removal and carbon buildup in the soil. Then finally we have the green cluster, which is probably the one we're more interested in, for the simple reason that it's the intermediate cluster where you have a reasonable amount of exposed soil throughout the year, so that you at least are able to get a few observations of your soil per year, and at the same time you have moderate to high rainfall, meaning that the sequestration potential and the plant litter breakdown into humus is very fast, or at least faster than in the red zone. So you have a good compromise between observability and monitoring capabilities from satellite and the potential to sequester carbon. So this is this is basically what's under the hood for the service of scoping areas of high sequestration potential. And this is done at country level now. But if you, in fact, if you zoom in a bit into the layer, you'll see that the kind of information we produce is extremely fine-grained and high resolution. Sometimes takes a bit of time to load. So here, let's go in closer. So you see that in fact we get an output at 10-meter resolution, so much higher resolution than most of the let's say regional, national, or global soil properties mapping efforts that have been done in the past. So this is really, we can still generate data output at a very large scale, but also ensure that we can get meaningful and relevant information at the field scale. And here you see that the generation of sequestration potential zones is also at the equivalent resolution to the imagery, which means you can really have a very fine-grained analysis on where you want to establish a project that aims to sequester carbon and generate carbon credits. The second service, or the second prototype of service, is the the optimizer for the field sampling locations. So in a similar fashion to what we did at the country scale in Kenya to generate these zones that were, let's say, delineating areas of sequestration potential for soil organic carbon, we do something similar but at the field scale, where we essentially also extract the bare soil pixels of the imagery. And then we perform an image decomposition, which sort of looks at the spectral feature space of the Sentinel-2 spectral bands and determines that there are, let's say, in this case, 6 different clusters of soil types, or at least of soil texture, composition, and anything which identifies the different pixels as belonging to different groups. And that basically gives us a lead into knowing where to sample. So we want to have samples that fall within all of these categories. Of course, that also fall within field areas, and not just any random soil, or at least it needs to fall inside of the project area. And then we can basically select through that feature space the ideal samples to take, and that basically produces an extent of data where in which we've selected the sampling points within each of these clusters, and even within these clusters we've selected we haven't selected outlier pixel values, but values which are far apart in that feature space to really cover all possible situations. And in this particular case, we've only generated about 30 point samples for a relatively small area, but I think we could even decide to sample fewer than that to be representative for the area that we want to estimate soil organic carbon for. And now, typically these points could be visited and sampled at, and then from year to year, you would keep the same sampling locations in order to be able to not only use that information to predict the soil organic carbon, but also to know at very specific locations what is actually the flux rates of carbon going in and out. That's also very valuable to know at point location to support the analysis. The next service consists of the actual soil organic carbon estimation. The only data that was available for prototype development was globally available data sets, such as the one made available by the ISRIC soil database, a data set called WOSIS. Very valuable, and has been collected since the 80s in the global tropics, and made available by the University of Wageningen, which is an amazing resource for our area of work. Unfortunately, the data are spread out in time. They're global in nature, so they're not targeting any project. But this is all the data that we had available to get started, and I think we're already seeing very promising results from that. Another data set which we use is the land degradation surveillance framework database, which is an effort by ICRAF based in Nairobi to also sample areas of degrading land in the global tropics, to be able to monitor those areas over time. So combining these two databases, we're actually able to create a soil organic carbon, at least spatial variability, a map of soil organic carbon. And this is something which, once again, combining the data, the bare soil composite data from Sentinel-2, alongside with the bare pixel frequency, we get to a topsoil estimation of soil organic carbon. And this topsoil estimation is, of course, giving information at the national level for global stock distribution. But if you zoom in at the field scale, once again, you will see spatial variability nuances offered by the product. So this is really a really powerful tool. You can actually see here the differential between the circular the circular field and its surrounding areas. And in this case, a darker shade means higher soil organic carbon values. Once again, because we've used a data set which is let's say a few years older than the satellite data that was used, I would only take the values here as a relative measure of soil organic carbon stock. So the differential between the darker and lighter plots is to be taken seriously, but the absolute amount that is given by the algorithm less so. And we can actually see, if we look at the bottom plot here, we plot the correlation between observed soil organic carbon content, so the actual measurements from those soil sample databases, and the predicted soil organic content, which is what the algorithm, the regression, has produced. And we see that there is a correlation, but this correlation is not following the vertical, it's not following the diagonal, because we get a systematic underestimation of prediction versus the observed values. So there is a correlation, but because we are basically not exposing extreme values and are not representing the spatial variability of soil organic carbon through soil sampling, it makes the exercise of soil organic carbon estimation more difficult. If the previous service that we explained about the optimization of field sampling location, if those principles were applied, we would actually get a much better correlation between the observed and predicted. But this is a very good first attempt at providing high resolution soil organic carbon spatial variability maps at country scale. But not only is it usable at the mesoscale and for country level statistics, it's also usable at project level and at field level for monitoring, reporting, verification purposes, and that's really where we want to. That's really where we want to. That's the market we want to target. If we look at other correlations, so if you remember the clusters of soil sequestration potential, which we will display here again, we have actually plotted the regression for the respective clusters. So for the red cluster, for the green cluster, and for the blue cluster. And we actually see that for the respective clusters, the typical, let's say, range of values for the sentinel to spectral bands differ. But we observe a level of correlation in all cases. And of course, the correlation is inverse, meaning that a brighter pixel is actually a proxy for lower soil organic carbon content, given that the observed pixel is bare, right? Because the darkness of the pixel might be due to let's say, stagnant water or more moisture. But in any case, a brighter pixel typically leads to a lower soil organic content value, which is what we observe because it's sloping, and the trend line is downsloping. The correlation is not obvious in all cases, but once again, we're using globally distributed data sets with relatively few sample points, many of them which are outdated and not optimized in terms of sampling location. So would we gather all these ingredients together? I think this soil organic content mapping exercise would be much more accurate and relevant. Final service that I still want to present to you today is the continuous monitoring of the land management practices, be it cropland management practices, or in this particular case, grassland management practices. Because we see the potential in sequestrating carbon in basically any landscape which can benefit from these MRV solutions, and we've identified that in the case of grasslands, there's relatively little interest in those landscapes, even though their sequestration potential is rather large, and at the very least, the offsetting potential is very large if their management is done in sustainable and regenerative ways. In this particular case, I took this. This is an area in just north of Mount Kenya, and we see, well, not let's say a few like 150 kilometers north of it, and we see that there's a clear division, a vertical division here in the rangelands, and it's actually a fence. So on one side we have a conserved or a grassland under conservation mandate, and on the right side an area under which is not under any conservation mandate. So it's already clear from the naked eye that there's a clear difference in how they look. But in actuality, what can we actually provide as information to help support monitoring, reporting, and verification of these landscapes in the purpose of generating carbon credits? Well, it's quite simple. In this particular case, we can generate a zonation of the degraded areas. But first, let me show you what is extracted from the bare soil composite. So you see that on the left-hand side, the area that I initially shown to you, there is hardly any exposed bare soil at any time in the year. A well-managed grassland should be that way, at least not in very arid areas, but in semi-arid landscapes like the areas north of Mount Kenya. This is really what you should be observing. You should not have much bare soil exposure in a grassland, because that's how you get maximum carbon sequestration through the grass root systems. In the case of the right-hand side, you see that actually the bare soil exposure is even far greater than what you saw in the normal composite, because the normal composite just shows you 1 pixel value at a certain time in the year, but this really maximizes the bare soil exposure, and we see that there's actually plenty of areas that are completely burnt out and bare at certain times in the year. And this is a kind of situation you want to avoid, and this is typically the result of overgrazing. So what we identified from those areas is the zones of particular degradation, or at least areas which should definitely be let's say restored and regenerated. But before we even get to implementing any regenerative practices in the landscape, it's already a good tool to indicate areas that have already degraded, and then as a result of that, finding out in the second step how much would it cost and how much carbon would we be able to sequestrate, and over which time span would we be able to sequestrate it if we regenerated this part of the grassland. But typically we want to find more grasslands that are healthy and establish new mandates to protect those, because that's really where the big gain is in semi-arid areas, in areas where agriculture cannot really be practiced, but where pastoralists have a big role to play to maintain grasslands in a healthy in a healthy state, and make sure that they remain that way. Yeah. So and this zonation layer is also done through decomposition of Sentinel-2 images to find out the areas that are barest and that have the least release the smallest signal of vegetation vigor in the span of 1 year. So through the illustration of these services, I hope you have understood the mission of SoilWatch to provide regenerative or to provide monitoring, reporting, verification services for regenerating soils and empowering landowners and land practitioners through carbon finance, and bridging the two together. And I really hope that through the exploitation of these large-scale open source satellite datasets, we can really make a leap forward in this industry and generate meaningful carbon credits that are effectively and truly capturing carbon in the soil and helping curb climate change. Thank you very much for listening.